So I have a couple of minutes left, and I'm going to step away from the particle physics a little bit and just talk about some of the applications. I gave you a lot of technological applications. I would just say a little bit more about accelerators that are developed in labs like CERN that are being used around in hospitals, for instance. So there are 17,000 accelerators operating in the world, roughly, as far as I don't know where Jim got this number from, but it sounds good. And around 9,000 of them are actually in medicine. And one of the things you can do as an example is hadron therapy, which is, so we're used to the idea that we give radiotherapy to kill tumours. If you want to kill a tumour with photons, you have to fire the photons through all the healthy tissue, and the way you focus on the tumour is just by rotating the patient and making sure the line of intersection is the tumour and it gets a bigger dose in the healthy tissue. But if you can use if you use protons, for instance, this is the energy deposition from a particle going through the body. If you can use protons or hadrons of a particular energy, the physical characteristics of the way they interact with the nuclei of the material of the atoms in our bodies means that once they have this very characteristic peak here, and they can dump all their energy in a very short, or most of their energy in a very short distance. And if you can tune the energy and the angle, you can make sure you can vastly reduce the dosage of radiation damage to the healthy tissue and really focus much more effectively on the tumour. And this is particularly important. There's a centre for this working on eye cancer in the UK because the eye's so delicate, you need this kind of thing. But it's actually got much wider applications, particularly, for instance, cancer in children, where it's really, really important not to damage the healthy growing tissue. These are hadrons. It's a Large Hadron Collider. Okay, they're very different accelerators doing this, but the fact is understanding this kind of physics is clearly having an impact on our everyday world. And the pathway through this kind of innovation, for instance, you can take for positron emission tomography. I'm out of time, so I should...
A couple of minutes.
Yeah, okay. But just to take very quickly one of these pathways through, a different one, positron emission tomography, where you inject patients with a tracer that undergoes a positive beta decay and produces a positron, which annihilates with an electron in the body and gives a very characteristic signal. Well, the positrons were basically predicted by Dirac's equation in 1928. He also solved the problem of spin as well, and antimatter, and basically the building block of quantum electrodynamics. The first cyclotron kicked off in 1932. The anti-electron was actually discovered, having been predicted here. The whole technology around constructing the radionuclides you need in order that decay in this way in order to be used in PET scanning, they're produced by these cyclotrons in hospitals. The cameras are using technology that's very, 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 very closely connected and basically comes out of medical detectors developed for nuclear and particle physics. So there's a whole pathway of stuff here, and this diagram that Jim's stolen from a study that's underway at the moment, where you see that the fundamental physics, in this case it was a theory ahead, predicted it, discover it, work all the way. You see that all the science on the side here, but you also see the kind of development that's needed on the way. For instance, there have to be tracers that are approved to be used by Medicare, and you have to be able to pay for this thing on Medicare in the US, otherwise it's not economically viable. Industry has to be able to build these things and make them cheap enough to be bought by hospitals and things. So there's a whole array of things have to work for innovation to come through, and the timescale is long, but nevertheless, without the fundamental science of the kind we're doing at the LHC, it doesn't happen. So I'll skip over that now. There's some numbers there. So I think the ingredients that drive innovation, as far as I can see, and this is one of the slides I just didn't change from Jim because I think he's absolutely right. Most of his slides were right, but I tweaked them. But we have a concrete project with ambitious goals and a deadline. We have highly competent, motivated teams right across, all the way from the management down to the PhD students, with the engineers off somewhere in the middle there. Or off to one side, actually, probably. The engineers have to be able to tell the management what to do when, quite often. The important thing is, though, there's this motivation to a common goal. Everyone's really working. No one can fire anyone, basically, on the Large Hadron Collider because we're all working for different universities, but we all have to be motivated by a common goal. We also then need open collaboration with competent partners. The universities, CERN is obviously the centre, but it has to work with universities and labs around the world and industrial partners for key technologies. We learn from each other and from others. We share the results freely and we pass them on again, the World Wide Web being the classic example, I guess. And we invest heavily in training and education. And we have all those ingredients at the Large Hadron Collider. So the project, the Accelerator and the experiments, it was conceived and designed to attack big science questions, and that gives you that common goal, if you like. The Large Hadron Collider and the experiments actually are at the frontiers of technology and engineering, every bit as much as they're at the frontier of our fundamental understanding of the universe. And international will to do something. It's quite remarkable that the changes of government. There's no single collaborating country that has the same government that it had when we started. The Accelerator and the experiments are unparalleled scientific instruments in many different ways. And so after 20 years of design and construction, we're really starting the data analysis here. Everything's going very well now after a glitch last year, although the experiments have actually worked very well from the beginning. And we're just beginning. We've basically, as you saw in that unification plot, this machine gives us access to a new landscape of fundamental physics, and we're just beginning that exploration. And it's only by doing this kind of frontier exploration that we gain the understanding of the universe that we, as human beings, we crave, but also which feeds innovation in other ways as well. Okay.